All right, I'm excited. We're diving even deeper into the weird world of statistics. I hope I didn't scare too many of you off. And I especially hope that this video doesn't finish the job. If you were flummoxed a little bit by the masses of maths that we had to cover, then I would suggest you stop this video right now and go listen to Sal Khan instead. The link is at the end of the last video and in the description of both this video and that one. Go and get yourself up to speed on the basic summary statistics, mean, median, ranges, etc. And that'll make tackling this video, which is about variance and independence, much easier. By variance and independence, I'm not talking about, the history of the United States of America. I'm talking about the relationships between different kinds of data, between different variables. So again, we are looking at these two variables. How much countries improved their economy between 1990 and 2013, which is the last date that I could find data, and how much they increased their carbon emissions over the same time. So this is a fairly knotty problem relating to the development of the world as a whole and how we can pull more lower income countries up to a modern standard of living and at the same time not melt ourselves and cause storms larger than a continent. If we can figure out how to solve those two things, then the future of the human race is probably looking okay. So let's talk about relationships, statistical relationships. I'm sorry for anybody who got excited, but I get excited about statistical relationships. What that means is, does this variable have anything to do with that other variable? Do they tend to move together or do they not? How would you even think about that? How would you even look at that? Well, here's one simple way. If you plot both variables on one chart, and here are those two variables from the last example, then we can start to think, are they related? What do you think? Well, the first thing I think in looking at this chart is that there's a couple of outliers that make the whole thing kind of squished into the bottom left-hand corner. So just focusing on the range there between sort of minus 100 and 200%, do you think these are related? By that, does it seem like as one goes up, the other goes up too? I'd say probably, right? The relationship seems to get more tenuous as the numbers increase. The relationship appears to be tighter down around zero. By the way, that's called heteroscedastic noise, and you don't need to learn what that is. So there's this fan happening, and it's tighter in the bottom left, and then broader up in the top right, maybe. And there does seem that as you increase one of these numbers, you do increase the other. Another thing that's interesting to look at here is that there seems to be this group of countries here that are either around zero carbon increase or just slightly below, but their GDP growth is small but positive, right? Somewhere up to about 50%. I would wager that those are the higher income countries that have started to do something about climate change in this period and whose emissions are not substantially higher than they were in 1990. So if we want to understand the relationship between these numbers in a stronger way than is possible than just looking at this chart, which tells us kinda, maybe, sorta, right? And even though Tukey said that being vague is an acceptable thing when exploring data, we don't want to be so vague that the best thing we can say is kinda, maybe, sorta. So let's focus on what a statistical relationship means and what we might be able to do about it. Did you know about the thermogenic effect of high seas piracy? If you look at this chart, it should be clear to say that as global average temperature has increased, the number of active pirates in the world has decreased markedly. So I think what we can say from this is that there is a clear relationship between piracy and combating global warming, and our best defense against a warming planet is to put on our tricorn hats and go raid the seas. I mean, obviously not, right? You can think about why there was a lower temperature in the 1860s and a higher number of pirates because before modern fossil fuels powered ocean-going vessels, it was a lot easier to be a pirate because nobody could catch up with you particularly quickly. Before GPS satellites, before radar, before aeroplanes, it was easier to have safe ports in small, scary islands out in the Caribbean where pirates would be able to freely dock without a national flag of registration on their vessels or whatever. Also, can we just talk for a second about how bad a chart this is? Why are the years on the chart rather than on the axis? If you actually look at the number of the number of pirates is the axis. This is probably the worst chart I've ever seen. There is a downward trend, by the way. You could have just done this chart properly, but they really wanted to both produce a terrible, spurious correlation, that is a fake statistical relationship, and a terrible data visualization. So let's look at a better data visualization of a statistical relationship. If you look between 2000 and 2009, at the number of people who died being tangled in their bed sheets, which, just for the record, is in the hundreds every year, and the per capita US cheese consumption, I think you can see a really interesting relationship, right? What's going on here? Does something need to be done? How about this? The total revenue generated by arcades, which for those of you who have maybe grown up in the Fortnite era, an arcade is when you actually had to go somewhere to play with somebody else's computer or gaming console because you didn't have one. It was a wild time. Arcade revenue has come up again, or at least came up again in 2005 to 2010. They had a bit of a resurgence. And at the same time, the number of computer science PhDs in the US was spiking. What's going on here? Are computer science PhDs somehow invading the arcades of the world? That seems almost workable, right? That seems like, unlike the last one that was absolute rubbish, this one seems almost like it might be true, right? Like, you think about it, there might be a relationship between arcades and computer science, because computer science PhDs, trust me, are pretty nerdy people. On average, they are probably going to be more likely to be patrons of a gaming arcade. But at the end of the day, this probably isn't true either. It just feels like it might be. Let's tackle another one. Per capita chicken consumption correlates with crude oil imports. Look, it went up in the early 2000s and then it went down in the late 2000s. This one is interesting because while I haven't really dug into this, I think both of these correlate with a third variable. How screwed is the US economy? What happened in 2008, 2009? Financial crisis. What happened in 2000, 2001? Financial crisis. That was the dot-com bubble for people who are too old to remember that one. This might actually be tracking a real relationship. But okay, here's a good one. The worldwide non-commercial space launches, so this is for scientific or military purposes, correlates with sociology doctorates in the US. What's going on there? And it's a very complicated relationship too. Look, they go up and they're down, they're up and they're down. Doesn't that show it's even more likely to be true? So I want to give thanks to Tyler Vegan's excellent website and book called Spurious Correlations, because of course all of these are rubbish, right? These are correlations. That means the numbers move together. They are not causal relationships. Causation means one thing caused the other one to happen. Correlation just means these things move together. Correlations can be caused by a whole bunch of different things. Some cases, they can be caused by a third variable. How is the US economy going? That might affect both of the things that you're interested in. Sometimes they can just be caused by pure noise. It turns out, if, as Tyler Vegan did, you just get thousands and thousands of variables, thousands and thousands of data points, and you compare which ones are like each other, it is statistically likely that some of them will be similar, but there'll not be any real reason behind it. They just seemed similar. It turns out if you get enough data, you can find patterns even if you weren't looking for them. This is something that our monkey brains are very much ill-equipped to handle. We are so good at spotting patterns. We can realize when there's something that's different to something else, or when two things look unusually alike. And in our evolutionary history, that skill has proven so valuable that we almost do it subconsciously. Remember back to the lecture on mapping, we talked about pre-attentive variables, things that stick out to you even before you consciously even realize it. They jump out of the page, almost like an optical illusion. That is your brain spotting patterns, spotting differences in patterns. Sometimes what it notices is just noise, is just nonsense. If you flip a coin 1,000 times, at some point you're going to get 5 or so heads in a row. 5 heads in a row is like what? A 1 in 32 chance? So in fact, you're likely to get, if you tip it 1,000 times, there's a 50-ish% chance you get 10 heads in a row. That's about a 1 in 1,000 chance, right? So you probably, maybe, let's say you do it 2,000 times, you'll probably get 10 heads in a row. And if you told someone, I got 10 heads in a row by flipping this coin, they're going to think, wow, that is not a fair coin. But the truth is, a fair coin actually would do that. Statistics is weird and exists in a space beyond our little squishy monkey brains, and we sometimes are not equipped for understanding what is a real relationship and what is a spurious one. So anytime you see a correlation, take it with a grain of salt. It may not mean one thing caused the other. It may not even mean that the third thing caused both of them. It may just be that someone looked at a whole bunch of data and some of that data was related. Because, yeah, the per capita cheese consumption in the US really does correlate with the number of people who died being tangled in their bed sheets. That's a real statistic. It's not a real relationship, but it is a real statistic. The only way to test for actual relationships between something, causal relationships where you know one thing influences another directly, rather than just there happening to be a relationship in the data, is to do controlled experiments. This is why medicine is so obsessed with randomized controlled trials, which is a form of strict scientific experiment where you say, we control everything else that we can that might affect this condition. And we have one group of people who get the medicine we're interested, and one group of people who get either a placebo, that is a fake medicine, or the existing best treatment. And does this one affect it? In next week's lecture, we're going to talk a little bit about how you can be so certain, just like how does science work? What's a hypothesis? How do you confirm it? What does it mean if you find a significant difference? I promise that one's not going to be as in detail on the math. It's going to be thinking more about the concept of how do we know what is true? Because it's really important to know that when we see relationships in data, we're only seeing correlations. As always, Randall Munro has a great joke about this in XKCD, which I'll give you a second to peruse because I always feel stupid reading out comics that I've put on my slides. If you don't read XKCD, you should start. What's a statistical relationship? Well, at the end of the day, the easiest way to think about that is, does knowing this one thing help me guess this other thing? Does knowing that a house is in Emu Plains help me know about its price? Probably a bit, right? Does knowing that a house is in Surrey Hills as opposed to Emu Plains help you know what it's going to cost? Yeah. It doesn't answer the question. There's still a huge range of prices in both of those locations. It's just that one of them you will know has reasonably affordable housing and the other one bloody doesn't. Does knowing that a student has gotten HDs in all of their courses last semester tell you their grade in this course now? No, it doesn't. But does it help you guess? If you had to guess, if you had to put money on whether they'd get an F, a P, a C, a D, or an HD, it would affect what you would be willing to put on the table, right? Either you'd be willing to put more money on the table or you'd change your guess up the spectrum if you knew someone got HDs before. And why is that? Because there is a statistical relationship between past academic performance and current academic performance. for anybody out there whose past performance is a little bit spotty, it's not 100%. You can still do great in this course and all of your other courses, regardless of what happened last year. But if we looked at someone's transcripts, it would make us more willing to place money on the table, more willing to guess. It would give us more information. The opposite of a statistical relationship, statistical independence, just means it doesn't help you. If I know someone's eye color, that doesn't tell me anything about their grades. If I know someone's country of origin, that doesn't tell me anything about their grades. Really, it doesn't. We're proud of that. If I know someone's name, it hopefully doesn't tell me anything about their grades. Sometimes institutional bias and racism and etc., sexism stuff creeps in on that one. But you would like to hope that if you knew someone's name, you wouldn't know their grades. If you know where someone lives, if you know if they live close to campus versus far away, you can make estimates about how they get to work. I live very close to campus. I ride my scooter here looking like a 12-year-old kid when I do. See if you can catch me getting on and off campus sometime. Whereas knowing how many books I own doesn't tell you that much, I would hope, about where I live. So to tackle the concept of covariance, which is just another way to think about correlation, the two are very similar. There is a mathematical difference, we're just not going to go into it. So we're going to talk about covariance, that's how things vary together. Well, first we need to understand what is variance. What does it mean when I say how a number varies? So we talked in the last video about what's the center of something, like where's the central tendency, where's the mean or the median. Variance is how much, on average, does it differ from the mean. That's literally the definition of variance. It is the average difference from the mean deviation from the mean. We often talk about this in terms of the standard deviation, which is a little bit different. It happens to be the square root of the variance. You don't need to worry about that at all. The standard deviation is a way of expressing how much data varies around the mean. And it is structured in such a way that if your data is normally distributed, then a bit over 2/3 of your data will be within one standard deviation of the mean. So between mean plus one standard deviation and mean minus one standard deviation. If you see that the mean is 5 and the standard deviation is 1, then that means that most of the data, just a bit over 2/3 of the data, is between 5 plus 1 and 5 minus 1. So between 4 and 6 is 2/3 of your data points. That is some quite tightly arranged data. If instead you had some data with a mean of 5 and a standard deviation of 3, then that means that actually most of your data is spread out between 2 and 8. So it's a bit more widely distributed. Again, this is only useful if your data is normal, as in follows a simple bell curve. You can always get an idea of how spread out your data is from the standard deviation. It's just this 2/3 thing is only true when your data mostly follows a bell curve. By the way, 2 standard deviations from the mean covers about 95%, 3 standard deviations from the mean covers about 99%, and so on. Standard deviation is usually referred to as sigma, lowercase Greek letter sigma. You don't have to do that. Covariance is how much does one variable's variance explain the other. So how much does the difference of this thing from its mean explain the difference of this thing? When this one varies up, does this one tend to vary up? When this one varies up, does this one tend to vary down? That's still a relationship, right? An inverse relationship. Or when this one goes up, it doesn't tell me anything about this one. It could go in all sorts of different directions. That is what covariance means. How much of this thing's variance can be explained when you know that other thing. So it's literally a mathematical encapsulation of how much does knowing this help me guess that. Let's look at that on our data set that we've been using as an example. So this again is a scatter plot of the percentage change in GDP from 1990 to 2013 on the y-axis and the percentage change in carbon emissions on the x-axis. Both of these are per capita, so normalized to population. The correlation between these two variables is 0.5, which is very strong. A correlation of 0 means they're independent. Correlation of above like 0.1, 0.2 means there's a relationship, and any correlation above 0.5, they're strongly related. If a correlation goes up to 1, it means they're the same. Every data point is exactly the same. That is, knowing one thing gives you perfect information about the other thing. When you know one variable, you always know the other variable. But what we're looking at here on our data is a strong correlation. And in fact, if you zoom in just on that bottom left-hand corner and you take out the outliers for a second, the correlation becomes even stronger. So the correlation is, of course, strongly affected by those few outliers. And if you look back at the outliers, most of them are either really big outliers in terms of GDP or really big outliers in terms of carbon, right? So there's a couple over here and there's a couple up here. That doesn't really say all that much. It just says that the correlation gets skewed slightly. So when we zoom in on that bottom left-hand corner, we see an 0.63, so an extremely strong correlation between these two. And if you think about it, yeah, as one goes up, the other one tends to go up too. And we can actually be more specific than that. You can actually calculate what percentage of their variance is explained by knowing the other variable. You can calculate how much knowing one variable helps you guess the other one. Explained variance is just correlation squared. So in this case, if the correlation is 0.5, so it is for this data set without the outliers removed, then that means that knowing GDP or knowing carbon means that the actual variance, the net variance of the other variable, is only 75% of what it was already. With the outliers removed, then we're looking at 40% of the variance being explained. So if we take those outliers out, and let's not question how sensible it is to remove China from any data set when you're looking at GDP and carbon, but if we were to take those outliers out from a pure statistic perspective and say they're not reflective of the relationship in the rest of the data, then we would be able to explain 40% of how carbon varies if we know GDP, or 40% of how GDP varies if we know carbon. So in other words, if we knew the standard deviation, we could reduce it by 40%, almost by half, just by knowing one of these other variables. If you were in a gambling situation, if you could reduce the variance of what you're gambling on by half, that would be worth a fair bit of money to you. That is a substantially better guessing scenario, and hopefully a substantially more profit-bearing one. I think it's much more helpful to think about actually how much less does this data vary as a consequence of knowing this other thing than it is to try and keep in my head what a correlation coefficient is and whether 0.5 is strong or weak or whatever. Anytime you see a correlation of 0.5, you know that that means that it's 25% of the way that one variable varies can be explained by the other. So that gives us our final piece of our puzzle of describing this data. We have our means, we have our medians, we have our quartiles, our minimums, and our maximums, and we can say we understand how each of these variables varies in itself, and also we understand that they tend to vary together. And looking at that gives us what we need to know to start finding insights, to start telling stories. At this point in an exploratory data analysis process, you might even have found your insight already. You might have even found the thing that you want to explain. Maybe what you want to explain is, hey, as this thing goes up, this other thing goes up. So now you have a correlation to back that. Or maybe the thing you want to say is, this thing tends to be higher than that other thing. So you can back that up by comparing means. These are explorations that give you just enough statistics. Again, hopefully everything I've drawn on here is something that you're at least vaguely familiar with from high school. And if you're only vaguely familiar with it, then please go get Sal Khan's help. He's a wizard at this stuff. These basic statistics give you, most of the time, enough of a picture about what some data is really doing that you will be able to competently and confidently put it into visualizations in a way that doesn't feel like you're just being overwhelmed by so many numbers that you have to get your head around all of them to understand what's happening. A couple of simple charts and these 6 or so numbers. This is the minimum level of statistics that you will need to succeed in this course, and I hope it was not too scary. So before I drop those links for Sal Khan again, I do want to show you, as is always the case with statistics, that actually you can't trust anything I just said. There are always ways to construct a data set that happens in those summary statistics to look exactly like another data set, but is completely different. This is a famous set of 4 charts called Anscombe's Quartet, named after statistician Anscombe. Each of them has the same mean. So this is a scatter plot, so each one has 2 variables. The x mean is the same. The y mean is the same. The x variance is the same. The y variance is the same. And the correlation between the 2 numbers is the same. But each of them is a completely different data set. In the first one, it's a bit like the data set we were just looking at. There's a noisy relationship between the 2 variables. That's probably what you expect when you see these numbers. When you see a correlation of 0.8, you see there's a really strong relationship. Oh, I'm doing that the wrong way. There's a really strong relationship between the x and y values in this first one. Moving on to the second one, there's kind of a relationship, but it's clearly not a linear relationship. There's clearly something else going on there. One increases and then decreases again with the other. In the third one, the bottom left, this guy here, there's an incredibly strong relationship, almost an exact relationship between the 2, almost no noise at all, but then there's one outlier that makes it seem like there's no makes it seem like the relationship is weaker, makes it seem like it's noisier. In reality, that looks to me like a perfect relationship with one wrong number, with one error in it somewhere. And then in the fourth one, this one's just wacky, right? All the data is exactly located at 8, and then there's one outlier off in the opposite direction. There's clearly no relationship here. In fact, one variable is just 8 all the time, except for one data point. That is nonsense. And if you try and create a mean or a standard deviation over that, of course you're going to get nonsense. Those measures are not designed to capture that kind of data. It doesn't look like any kind of real world data at all. You need to be careful. A little bit. This is why it helps to do visualizations. Visualizations would pick this up instantly. You can't just rely on the numbers, says Anscombe. And he's right. You need to do visualizations too. Combine the plot with looking at these simple descriptive statistics, and you'll be able to get a much bigger picture of what your data is doing than by looking at either of the things alone. So again, and actually I might encourage everybody to do this. If I just freaked you out, even if you're relatively confident in what I just said, but you think you would benefit from a bit of a refresher course, do go and check out the Khan Academy page on summarizing quantitative data. It explains more eloquently than I ever could the simple things that you need to know to get through this course. And to be honest, the simple things that you need to know to be a capable practitioner with data in industry. Go check that out. I'm going to effectively say it's homework for this week. I'm of course not going to mark any of it, but you would be silly to not at least go and watch a couple of videos, if not even do some of the exercises. It will make you feel more confident that you know what you are doing. And let me tell you, there is going to be a strong statistical relationship between people who understand statistical relationships and people who do well in this class. I hope I have done my best to make it something that you feel that you can learn, because I've got to be honest, I love this stuff. It is fun. Once you get over the hump of the different nomenclature and the different way of working, the different language, it gives you so much more of a window into what the world is actually like. It does not in any way make you less of a designer to be more of a mathematician.